Good evening. Our subject for today will be Cronbach's alpha. This is a measure of internal consistency, not the only one, of course, and we'll touch on one or two other methods as we go, but it's the main event. So uh, primarily, we're concerned with how to get Cronbach's alpha if you need to calculate this by hand. Okay, so this is a step beyond the split half method, which we covered in an earlier presentation. So as you should know by now, the split half method gives us an estimate of the internal consistency of a test. Generally speaking, it works pretty well, but because we're only dividing the test crudely into two halves in a relatively arbitrary fashion, we can't be sure that the split we did really captures the internal consistency of the measure. Now, in theory, you could, for every item on the test, calculate its correlation with every other item on the test and take the average of all those correlations, and then use the good old Spearman-Brown prophecy formula to get a more precise estimate. But yeah, no, let's not and say we did. That would be very tedious, especially with tests that have 30, 40, or 50 items on them. So, what the clever psychometricians of the early to mid 20th century set out to do was to develop a more general formula that could be used to accomplish the same goal without going through all of that process and enabling us to move past the relatively crude split half method. And the two best known solutions to this problem were the Kuder-Richardson Formula 20, KR20, introduced in 1937, and Cronbach's coefficient alpha, or just alpha for short, introduced in 1951. I want to say a few words about the Kuder-Richardson formula. By the way, formula number 20 kind of gives you a hint that the paper in which this was presented included quite a few reliability equations. They were working their way through a whole mathematical argument about the nature of tests and reliability and so forth. Of all the equations in the paper, though, KR20 and to a lesser extent KR21 are the ones that caught on as being generally useful. It does, in fact, give you the mean of all the possible split half reliabilities that could be generated for a test, and it does it in one pretty easy formula. It's not that difficult to crunch this number by hand. There is, though, an important limitation on KR20. It only works if the test items are scored dichotomously. So if, for example, you have items that can either be correct or incorrect, you're all set. If it's a personality scale where you're saying that things are true or false of you, or that yes or no, you agree or disagree with a particular statement, then it works fine. But if you have any more complex kind of scoring system, like you're using Likert type scales where people are rating their agreement or disagreement with statements on a 5-point scale, you literally can't make it work. There's nothing you can do here. We won't actually be learning to calculate KR20 here, but you should be aware that it exists because you do see it used. And so you'll be reading a paper, in a journal somewhere, and the authors will say, and the reliability of the test, based on Kuder-Richardson Formula 20 was acceptable, or they'll just put KR20 equals, 0.88 or something, and you're supposed to know what that means. Our main event is Cronbach's alpha. Which was introduced about 14 years later in a paper authored by, guess who, Lee Cronbach. And this is a broader, more general solution to the same problem that Kuder and Richardson had been tackling a generation earlier. You can use this whenever you can use KR20, but you also can use it if the items are being scored, say, on a 3-point scale, wrong, halfway there, correct, or a 5-point Likert type scale, or a 10-point scale, or anything else. There is an underlying assumption here that all the items are about equally likely to be answered, in the keyed direction. Most researchers pretty much ignore that. It's rarely going to get you into trouble. So what I would say is don't worry about it unless you encounter the insane reviewer number 2 for your paper, and then you'll have to jump through some hoops and convince them that what you did is okay or do something else. For that, go to a more advanced seminar. Again, very few authors of even journal articles published in top professional journals really fuss about that. This is, I would say, hands down, the most widely reported reliability statistic. You see it in papers everywhere. It is so well known that people often don't bother saying Cronbach's alpha or coefficient alpha. They'll just put, the reliability of the test was good. Alpha equals 0.84. And the assumption is that you know what that means just about as well as you know that the italicized R means a correlation coefficient calculated the way Pearson first did. And we don't bother writing Pearson product moment correlation coefficient either. All right, so there's the equation. And, in terms of my assessment class geared towards advanced undergraduates, this is the most complicated looking one that we have to deal with. So take a deep breath and don't let the anxiety get to you too much. It's actually not that hard to work with as long as you just do it calmly step by step and follow the proper order of operations. If you, deviate from the proper order of operations, you're dead. That just always kills you. If you cut steps or write sloppily, it's really easy to make errors here. The formula, by the way, can be represented in different ways. I've come to feel that this is the easiest one to read. So we're trying to solve for alpha. And again, alpha is simply the reliability in terms of internal consistency of the test data that we're working with. The first little section here, k over k minus 1, well, k is simply the number of items on the test. There is an easy error to fall into here. You could think that it means something to do with the number of people who took the test, and it doesn't. If it's a 10-item scale, k is 10. I don't care whether 50 or 500 people took it. It makes a little adjustment happen. It's not a major driver of the results, but it has to be included. 1, of course, is the number 1. And we are subtracting from the number 1 this complicated looking thing. S squared sub I is representing the variance of a single item on the test, item I. Sigma simply means sum of. So this sigma S squared sub I or S sub I squared represents the sum of the individual item variances. We'll circle back to that. But what you have to remember is that each item is a test in its own right. S sub t squared is the variance of the total test scores. I'm not sure whether old Lee meant this to stand for total or test. I think test, but it doesn't matter. So that's the variance of the scores on the entire test. That's it. That's it. That's enough, isn't it? So, how do we calculate it? Well, first thing you're going to have to do is to compute the variance for each individual item on the test. Again, I will circle back to that, but this needs to be done, most easily done on a spreadsheet rather than by hand. But if you must, you must. It's still easier than correlating everything with everything else. You also, of course, need the variance for test scores, which is pretty straightforward. You've got the scores and you calculate or have the spreadsheet calculate the variance. Then you're going to divide the sum of item variances by the total test variance. Total test variance is virtually always greater because it includes all the individual items plus whatever is shared across items. Again, I'll circle back to that. So the result at step 3 should be less than 1. There are occasional exceptions. They're very rare. They're never big. So if you get some number that's in the negative range, go back and check. You may have flipped the 2 variables there. Then we're going to subtract that from 1. Now, again, if you're doing all this by hand, it's very easy to kind of be hasty and forget about that. Don't forget about it. It'll mess you up, and you won't realize that you've messed up until later. So we have the sum of item variances divided by total test variance. We now subtract that from 1, and we multiply it times the number of items on the test and divide that by 1 minus the number of items on the test. By the way, if you prefer to do the number of items divided by 1 minus the number of items first, and then multiply that times what you get after step 4, fine, it works just as well. So again, just briefly, here's what's supposed to be going on here. Each test item is a measurement. What we're doing in creating a test made up of many items is asserting that all of the items, to some extent, are measuring the same thing. So I'm testing you on one thing, which could be, how well you learn psychometrics. It could be how extroverted you are. The whole test is supposed to be about that. So each item is supposed to be contributing to that overall measurement. Now, when you score the item for a bunch of people who took the test, there's going to be some variance, unless everybody answers it in the same direction, then the variance is 0. But if you have some people saying yes and some no, or some people getting different scores, there will be variance. Now, just zero in on that. What's variance for the individual item, like item 4? What's that measuring? Part of it is, of course, random error, noise. That's always there. Part of it is something that is unique to just that item. It's something that item is tapping into all by itself, that it doesn't share with any other item on the test. That's also not what we're really interested in. And part of it is what we call shared variance. This is something that item is measuring that other test items are also measuring. In a sense, this is just another way of saying that the items correlate with one another. To the extent that they correlate with one another, they're doing the same thing. They're sharing variance. A test is internally consistent, cohesive, to the extent that this shared variance dominates the picture. In other words, the more strongly the test items correlate with one another, the more we can say they're measuring the same thing, at least to some degree. Now, if you really look closely at that equation, you can perhaps see that that's what's really driving the results. But you don't need to see that. You don't need to have that intuition to make it work. Crunching the numbers is relatively easy. There again is the formula. And again, notice that the proportion of item variance to total test variance is a key driver here. Okay, so how do we calculate it? Here's an example, a real test, by the way, but I made up the data here. There's a measure developed by Ed Diener out in Indiana called the Satisfaction with Life Scale. It's a 5-item scale. It's been very widely researched. You can look it up sometime. And so let's pretend we've given it to a sample of 80 people as part of a study. And we want to know how reliable the Satisfaction with Life Scale was in this sample. All right, so we score it and we put all the numbers into a spreadsheet. I will be showing you a spreadsheet shortly. And we find that the individual item variances are 4.2, 5.1, 3.8, et cetera. These again are make-believe data. And we add all of those up and we get 25. It's always fun making up examples for class because everything can come out nice and even, right? The variance of total test scores happens to be 75. Notice again, it's nearly always going to be the case that total test variance is greater than the sum of individual item variances because the individual items are part of the test. So it's items plus whatever items share. So we divide 25 by 75 and we get 0.333. Go as far as you want with that. 3 places to the right of the decimal is probably plenty. We subtract that from 1 and we get 0.667. multiply that times 5 because we had 5 items, and we have 3.335. Divide that by 4, 5 minus 1 being 4, and we get 0.834, which, at that stage, we may as well round it to 2 places. So we would say the reliability is alpha equals 0.83. That would be it. So that is a number of steps, but each step is pretty easy once you have the raw data to work with. So let's have us walk through another. And in this case, I'll ask you to kind of set the equation up if you can. I've done one thing for you. I added up the item variances. Again, this is fictitious. These are fictitious data. So the sum of item variances is 7.65. So if you are setting up the equation, that would be in the numerator of that fraction way off to the right. The variance of total test scores is 18.5. So that would be in the denominator there. And of course, K is 20. So if you can, try to set that up on your little piece of scratch paper there. Having your handy dandy calculator handy would be a very good idea, because dividing 7.65 by 18.5 is, a bit of a nuisance. If you have your calculator and you've done that, you'll see that the solution is about 0.414. So we now have 20 over 19, if we can make that step happen quickly, times 1 minus 0.414. So you would subtract to get 0.586, and you would then multiply. The end result should be 0.617, which we could round to 0.62. And I'll tell you what, let's look at this on a whiteboard together, and we'll see how it goes. So we had, in the first set of parentheses, 20, the number of items on the test. You have to bear with my handwriting here. I'm trying to do this with a mouse. Over 20 minus 1. Oh, there we go. I'll erase that little dot. It's bothering. Oh, if I erased the 1 instead. Draw 1. And we're multiplying that times 1 minus, what was it now? 7.65. Again, bear with my handwriting. Over 18.5. And we go like so. Okay, and we're trying to solve for alpha. So what does this equal? Well, let's see. We'll keep the 20 over 19 here. Again, I hope everyone sees that 20 minus 1 would be 19. And over here, we're going to do the division problem. And again, use your handy dandy calculator by all means, unless you really love doing long division. And we get approximately 0.414. It's rarely worth going more than 3 places to the right of the decimal in psychology research or educational research. Our measurements aren't that precise after all. Okay, well, that's going to be equivalent to 20 over 19, keeping this going in its own little set of parentheses here, times 0.586, which in turn will be equal to, I'm going to run out of space if I keep going to the right here, but 20 over 19 would work out to 1.053. Again, at this stage, it really doesn't matter whether you do that first and then multiply, or just multiply and divide. But since I have it set up visibly the way it is, we'll follow the rule of do the stuff in the parentheses first. So it's equal to 1.053 times 0.586. And again, unless you love doing long, division by hand, which you should feel free to do, if you use your little calculator, you'll see that this comes to 0.617. And again, rounding off to 0.62 is just fine at the end of the day, unless you want to stay 3 to the right, and then that's allowed. Okay, back to the slides. Here we go. That's getting up to wrapping up. So you know what, before we wrap up, let me change to a different share, and I'm going to go for a spreadsheet, but I need to just open it up. Hold on just a moment. And here we go. Okay, back to you. And we're going to open up a data set that is available for my students to work with. Let's see, here we go. You're seeing it. I'm just making it nice and big now. Okay, so what we have here are data on a great many people, actually, who took a multiple choice measure of sort of general knowledge about the world. And so here, just to orient you to it, each column beginning with column F is an item on the test, item 1, IO1, item 2, IO2, and so forth, all the way across to item 32. And then the score in column AL here is simply the sum. You can see that in the formula bar that I'm showing you over here. It's the sum of the individual items. So we can use the spreadsheet to score the test very simply. It's just a formula sum of F2 to AK2 covered that range. Now, as we scroll down quickly to the bottom, again, you see this is something you would not want to have to do by hand, right? You've got a nice big data set here. If you look at row 744, you'll see that I've labeled it variance. And what I've entered into this first cell is the equation that this equals VAR, which is the Excel way of saying variance, open parentheses, from F2, the first line first row where you had data, down to F731, the very last one, close parentheses, and there you go. If you wish, by the way, if you start to enter a formula, in fact, I'll do it down, the next one down, you'll see that it often suggests ideas of what you might be after. So we'll just say, oh, I wanted to do variance. And well, this is giving us an old form, but that's fine. We're doing the variance, and I'm saying F2 to F731, and poof, there it is. I can then change the format if I wish to make sure that I have something to the right of the decimal. That's just for it looking pretty visually. Now, importantly, when I do that, I mean, I've now gotten the variance for one item pretty quickly, but I don't really want to enter that formula 32 times. So again, as some of you may already know, what I can do within a spreadsheet environment is to select a cell that has a formula in it and kind of paint across from there, and then use in the upper right part of the home menu, there's a lovely function called fill. Now, I just went from a certain cell over to the right, so I'm just going to say fill right. And what it does is to replicate the same equation, but changing the location to match the new cell that you're in. So when I'm here over in M744, the replication of the equation automatically made it be the variance of M2 to M731. Incidentally, as a little side note, you'll be wondering perhaps why there's no variance on the earliest items. This is a test that's designed to go from very easy items to very difficult items in a pretty systematic order. So the very first few items are so easy that none of the 730 people got the wrong answer, basically. But as you work your way across, you see there's more variance because there are people with both right and wrong answers. What did I do all the way to the right here? Well, here I calculated the variance of the total test score. Column AL here contains the total test score. So this is the variance of total test scores, or S squared sub T. And down underneath it, I added together, summed the variances for each of the individual items along the way. And that gave me the sum of individual item variances. Now, if you're a student in my class, I would always give you the total test variance, and I would either give you all of the item variances where you just add them up, or in some cases, I might even give you the sum of item variances. But if you're doing this on your own at some point, this is a way of getting these figures. And with them, you now know how to derive Cronbach's alpha without a great deal of more fuss and bother. As we duck back into the slides just for a moment, remember, internal consistency is the most widely reported form of reliability. You see this in virtually every paper you'll read that involves test data of any kind. Reasons for this are dual. It is applicable to the large majority, really, of the tests that we use. We more often than not include multiple items, after all. And, it's not that hard. You don't have to have people come into your lab over and over. There's just not a lot of fuss here. The split half method, Kuder-Richardson Formula 20, Cronbach's alpha, they're all okay. They're all appropriate, although KR20 and alpha are generally considered superior to split half reliability for most purposes. Generally, Cronbach's alpha is the one you're going to see all the time because it is the most general solution to the problem and just has really caught on in a big way. That said, we are done for now, and I want to thank you for your time and say good night.